Ladies and gentlemen, welcome to the very first keynote of ICSE 2021. I am very pleased that we found Dario Gil willing to deliver this first keynote. Dario is originally from Madrid, but right now he is Senior Vice President at IBM and Director of IBM Research. He has been Vice President AI and Quantum, two topics that will recur in his keynote. Under his leadership, IBM was the first company in the world to build programmable quantum computers and make them universally available through the cloud. Several of you may have used Qiskit, IBM's open source quantum SDK. In 2003, Dario obtained his PhD in electrical engineering and computer science from MIT, and he has published widely on lithography. He's a member of the National Science Board, which is the governing body of the National Science Foundation, and a member of the Board of Governors of the New York Academy of Sciences, and a trustee of the New York Hall of Science. Concerning this keynote, the logistics of the keynote, please feel free to enter questions in the chat. I will monitor them and possibly group them. If you like a question, please feel free to add a thumbs up or a heart to the question, so I know that there are more people caring about the answer. We will answer the questions at the end of the talk, but you're welcome to enter them as the talk progresses. In short, it is a great honor to have Dario Gil as speaker here at ICSE 2021, and I happily give the floor to Dario. Dario, here you go.
Thank you very much, and good morning and good afternoon to all of you, and thank you very much for the invitation and for allowing me to spend a few minutes with you. Since we cannot be together in person, I thought I would at least situate you geographically from where I'm speaking. This is the research headquarters of IBM, the T.J. Watson Research Laboratory. It's about 45 minutes north of New York City. And this is my home, and it's a beautiful building that was designed by Eero Saarinen, and it's part of a global network of laboratories that compose IBM Research that I'm illustrating here on the map. We have about 3,000 scientists and engineers distributed across all of these locations, and we've operated a research division for 76 years. So we have always a long commitment to science that has driven a lot of fundamental understanding, including Nobel Prize winning work, and a variety of disciplines that are devoted. The reason why we come together in the context of IBM Research is to always explore what's next in the world of information, new ways to store and process information. It's an eclectic group of physicists and mathematicians and computer scientists, and then domain specialists. And today, we're going to get a chance to talk about AI and quantum computing and the implication to software. But we have a broad set of activities also in the world of semiconductors and systems, cloud, and as well as cryptography and security. But as I mentioned, the unifying theme of the work that we do is to explore what's next. And I actually think that we live in the most exciting time in computing in the last 50, 60 years, really since the time of Claude Shannon and Alan Turing, et cetera, with the advent of computers and the foundational construct of information theory. And the reason is because of a convergence and the implications of a convergence of a set of technologies, which I neatly summarize as bits plus neurons plus qubits. The world of high precision computation embodied in our high performance computers, broadly speaking, the world of bits, the biologically influenced information representation that is expressed in the world of neurons and neural architectures, and the physics induce implications to information that is embodied in the world of qubits. And today, I would like to touch on two of these dimensions. First, what are the implications of the advances that we have seen in the world of AI and large-scale neural networks, particularly expressed in the form of natural language processing, and the implications that it will have to the language of machines, of code. And then I'd like also to touch and discuss what is, briefly happening in the world of software as far as quantum computers go, and share with you a couple of projects on each of these areas for discussion and for your engagement. So let me start with discussing some of the implications of AI to the world of software. I need not tell this audience, since you're like world leaders, pushing the forefront of the world of software, of the implications that it has in society at large and in businesses the world over. It is interesting to reflect on the role of AI on being embedded in software all over the world, but also of what are the opportunities that AI may present in allowing us to program and to write code in a better fashion. And if we look at what was the trifecta that enabled the last 8-10 years of progress in AI, we're all familiar that it was the intersection of large data sets for training, sufficient computing power to train at scale the large neural networks, and algorithmic advances that have continued to propel the advances of AI. So we're going to ask the question today of what kind of data sets would we require to enable a similar kinds of achievement for the world of code itself. And it is popularly understood that, for example, the role of data sets in the advancement of AI was deeply profound. And ImageNet is, of course, a good example of how the curation of a large-scale data set, in this case, a transition from having about 3 million images and 5,000 classes to over 14 million images and 22,000 classes, combined with the utilization of the right computing power in 2012, drove the most significant advance in computer vision from the perspective of labeling that had happened in the history of the field. And ever since that, we have seen sort of like the continued progression of like the error rate, as an example, for the narrow task of image classification for well-defined problems, as an example. We've also seen, of course, that we can keep pushing the boundaries of what is possible with these kind of systems to do all sorts of nifty demonstrations and broad-scale applications, including, I'll highlight as an example that it was just recently published, the results on the cover of Nature, of a project that we had created to build a machine that was capable of engaging with humans in live debates. And so it's kind of a fascinating demonstration of the possibilities of, albeit a narrow form of AI, of what is possible at advancing the field. But today we're going to preoccupy ourselves with how can we use some of that power for the world of code and helping us write better code and enable the productivity and the scale of software through business. And we are familiar with the fact that there's a massive shortage of software developers around the world. I give some numbers here. This is probably a couple of years old, so a little bit dated perhaps, but still, significant that there's hundreds of thousands, for example, of shortage developers in the US. Very large numbers of shortage, over 150,000 of data scientists, and then there's a massive growth in demand, right? That we know as the evolution of each enterprise. In fact, also, you can estimate some of the implications of code to the economy, that roughly, close to $500 billion is spent annually debugging code. And if you look at the portion of IT spend allocated to things like quality assurance, can be close to 40%. So we know this, and let's quantify it, more concretely, that, we also have a massive amount of legacy code that is, often in needs of modernization. Some of these systems and applications may be running, but for example, if some of you followed during the time of the early onsets of the pandemic, when there was a need to greatly expand, the unemployment benefits in some local geographies in the United States, there were a number of articles that were reading that were discussing about the need for more COBOL coders. In the context of the coronavirus fights, because there had been, applications, legacy applications that have been present in some of these government agencies that had never been modernized. So if you actually look under the covers, there is over 220 billion lines of legacy COBOL that has never been, modernized. And the cost associated with this it's somewhere around, I think it's between 30 and 50 cents per line of code. It's a reasonable estimate of modernization. So, you multiply those two numbers together, you're talking just alone on this space, $100 billion opportunity as well. So it's really, and the challenge here is a skills gap, obviously, right? The majority of contemporary developers will program in Python, etc., Java, C++, but not so much in some of these languages. So one of the challenges that we're very excited about is what are the opportunities of applying AI to modernize legacy code. So how could we go about doing that? Well, just to have a little bit more of an abstract reflection is that, the recognition that symbols, by and large, allow us to acquire, represent, share, and communicate knowledge. So we have gotten accustomed to think about the opportunities of applying NLP and transformers and the latest advances in neural networks to the symbols of, or human languages of English and, and Spanish, etc. But of course, symbols can be the diagrammatic symbols of chemistry, or it could be, the symbols that come from sensors, or it could be the symbols that are part of our programming languages, or the equations of physics. All of them represent symbols. So there's no reason why those abstractions cannot be or benefit from these advances that are happening in AI. So we are taking a perspective within IBM that, one of our core priorities of advancing AI is to apply to languages writ large. Languages as the embodiment of these symbolic systems through which humans have communicated. And we're talking about the world of chemistry or storytelling or imagery, or, as we're going to discuss today, the world of code. So let's apply a little bit of the playbook of what we saw in the last decade when we've made significant progress on the language of humans. So we have seen, as an example, that when we've applied AI to human language, and if you measure it, for example, on speech performance, as in the y-axis, you see the word error rate and sort of the improvements over time as we had, not only algorithmic improvements, but fundamentally more and more data with which to train these systems, we've seen dramatic improvements. So now we have built a massive repository of NLP and software artifacts, also, automated reasoning and decision-making techniques, and significant advances on explainable AI, which is also going to be very, very important in the world of code for being able to debug and understand what the software is doing. So what would it take to, we ask ourselves, to create the equivalent of an ImageNet for code? And the breakthroughs that we could enable if we had such a large data set could include everything from, using it to do code language translation, just like we've done the statistical approaches of translating between human languages, areas like code search and retrieval, similarity analysis, improvement of performance, code memory improvements, as well as code classification. So we were really excited after a gargantuan engineering effort that we released last week, something called Project Codenet that you can find on GitHub, and I put the link below. And this is a really high quality code data set for algorithmic innovation and benchmarking. It's a large scale data set that has been curated with 14 million code samples, over 4,000 code problems, encompassing 55 programming languages and 500 million lines of code. It's very diverse in terms of the problems and codes that is represented in here. And importantly, the codes are well tested, and test sets are provided for each problem. So there's a very significant amount of annotation that has been created to enable the community to benefit from this large effort. It is without a doubt at present the largest AI for code open source data set available today. And there's a huge diversity of solutions for each type of problem. So 80% of the problems that that have been created and shared have more than 100 solutions each. So if you look at the bar graph on the right-hand side, there is about problems. You're seeing here the number of problems that have at least n solutions. So problems with more than 10 solutions, you have 4,000 of those, and problems with more than 500 solutions, you have over 2,000 of those. And then also representing a whole variety of languages, which presents a lot of creativity potential for this community and others to explore the possibilities of then applying the advanced AI techniques, given this data set. More broadly, we can think about creating an AI for code stack that would touch everything from the data sets that would be required. And here we're talking about from code repositories to logs to test suites to configuration files and data models are all things that would be relevant to this task. You have then an ingestion layer around it that is needed to do things like data labeling, etc. You have a layer of representation with intermediate representations to allow then the core algorithms, the NLP-inspired AI techniques to do things like embeddings, etc., to be applied to them once they are properly represented. And then you have the oriented sort of objectives of being able then to create environments that are well suited to understand, review, retrieve, and generate and test and verify code. And ultimately, you get to the application layers for the productivity enhancement to be able to do things like application vulnerability or modernization efforts or customer support in terms of bug tracking and routing, etc. So this is a fantastically creative and an opportunity for all of the community to build a complete stack that would have the ultimate result of greatly increasing the productivity and the quality of the code that gets written. Just to give as an example, if I was just to pick one of the categories at the very top, application modernization, I'll show you an example of a project that we have done with a very large car manufacturer, in which, in this case, they had an application, and as you all know, enterprises will have thousands of applications, right, running at any given time, many in need of modernization. But in this case, there was a mission-critical application. It's about a $200 million asset with over 3,500 Java files and more than 1 million lines of code. The application itself had a multi-generation sort of like legacy of Java tech built over a decade. And there had been a significant effort with architects and other ones to undergo sort of a manual migration effort. And here's where we engage to apply some of these core techniques of AI for code for modernization. And the compression can be very significant, right? The parallel effort here to demonstrate the possibilities so that we could do kind of like an A/B testing. We're talking about the recommendation in terms of how to segment the code and the classes for modernization. The effort got shrunk to 4 weeks versus a year. It automatically defined the partitions to be able to migrate and evolve into microservices. And this, in this case, the analysis was done leveraging both the runtime and the data dependency analysis to understand even like what parts of the code were not being utilized. So it actually surfaced a significant amount of potential dead code that also could be eliminated. So it's just like touching the tip of the iceberg of the opportunity of what's going to be possible. So I'm excited about this opportunity, right, for all of this community to advance on continuing to create large-scale curated data sets. I hope that many of you will find valuable Project Codenet and you will consider contributing and enhancing for the benefit of the community of what's going to be possible with AI. So that's one pointer. The second one is I touch on then we need the right AI for code algorithm stack. I'm sure many of you are also advancing multiple dimensions of what's going to be possible here. And then, of course, we want to be able to apply these techniques to be able to derive business and societal value. And, I highlighted the point that modernizing legacy code to boost developer productivity is something that is an urgent priority. So that's topic number one that I wanted to be able to discuss, the world of neurons and the world of neural networks and the application for AI for code. Today, I want to touch also a second dimension that I think is very exciting on what is occurring in the world of software, and that is the emergence of quantum systems. We know from an information theory perspective that we could segment the classes of problems that we can tackle with computing in easy problems, things that don't sort of explode in algorithmic complexity due to the number of variables present. But we also know that we have hard problems for classical computing. There are many different bounds of hardness. One famous example, of course, is NP hard problems, but not exclusively. There's many different types of hard problems. And we also know that quantum computers are going to alter the equation of what's easy and what is hard. Now, quantum computers will not solve all hard problems, but they have the potential to impact a number of really relevant and important hard problems, including the world of simulating the natural world, problems in physics and chemistry, problems related to even machine learning, problems related to factoring and also optimization. So if we were to sort of summarize, broadly speaking, the applications, the core kernel of value inside a quantum program is something called a quantum circuit, and that is the core currency of quantum computing. And you're seeing here a representation of an illustration of what a quantum circuit looks like. And you can just simply think about it as the set of operations, logical operations that we get to do in quantum world that, some of them may be very hard or impossible to do in classical world. In classical world, in the end, we're accustomed to the idea that behind the scenes, we have ands and ors and nots. Well, in quantum world, we have some of those operations, but we have some extra ones, right? Things like, the opportunity to do interference and entanglement and core physics properties in the representation of information. Well, the trick is then, of course, to be able to construct these quantum circuits and apply to classes of problems that are relevant. There are three broad categories where the field is exploring the implications of these quantum circuits. One is the original Richard Feynman idea of applying building a computer that works like nature to simulate nature. We know that nature obeys the laws of quantum mechanics. So therefore, if one is to model a physical system or chemistry or material science that is actually behaving according to the laws of quantum mechanics, if you have a machine that behaves like nature does, it's going to be easier to simulate and model nature. So that's one class of problems where there's a lot of focus and excitement. A second class of problem are algebraic problems, which of course are the underpinnings of areas like machine learning and differential equations, as well as things like factoring. And the third category are search problems, traversing graphs, sampling from a distribution, like doing things like Monte Carlo, as well as other kinds of graph problems. So these are the three core areas where the field is exploring the opportunities and advancing in quantum computers for this space. To give you a brief intuition for how an algorithm works in quantum, it works the following way. And today I'm not going to try to sort of like explain, all the elements of what's behind a quantum computer, but just to give you a flavor, a taste for what goes on. What happens is at the beginning, what we get to do is we get to put the quantum computer in a superposition of all the available states. The number of states that we get to have present in a quantum computer goes as 2 to the n, where n is the number of qubits. And so, as an example, if we have a 2-qubit system, we get to have 4 states. Visual way to represent it, imagine you have a sphere like you see here listed. And now in a classical world, like the states that you would have at any given time would be, let's say on the North Pole, you could put like one of those little pink spheres, pink little moons in the North Pole. Let's say we would call that a 0. If you put in the South Pole, you would call it a 1. But in quantum world, we get to actually put those little moons all over the sphere, right? Not only in the North and the South Pole, so we could put it in the equator as an example, and that would be a superposition of 0 and 1. But we could put it anywhere in this sphere. So that's the first thing we do, right? We put the computer in a superposition. So we have a 50-qubit quantum computer. You get to have 2 to the 50 states. The second piece that we do is you inject the problem into the quantum computer. What this means in practice, to grossly simplify it, is actually to inject a phase into these states. So these little moons that are in my sphere, I can also rotate them, right? So here, that's what's depicted by the blue and the pink moons. so they can be rotated, and that is the encoding that we do with the data. We engage in these rotations. And then the magic and the magical operation that happens inside the quantum computer is that because these states have now an amplitude and a phase, what a quantum circuit does is the evolution of these states such that we can interfere the amplitude and phases of these different states in such a way that the right answer gets maximized, and then you collect a measurement, and then you get the right answer, right? So you get to sort of do this amplification through interference. The only point to bring forth here is notice how different it is than the classical operations that we do. We don't get to be able to do this, entanglement, operations and interference steps that are present in quantum computers in a classical world. So how does one go about programming these computers? Well, just until a few years ago, relatively speaking, 5-6 years ago, programming a quantum computer looked like the right-hand side. That's a picture of Jerry Chow, who leads our experimental quantum computing efforts, in front of room temperature electronics, dialing in the microwave pulses that get used to be able to send into the quantum computer to create these states. So in some way, it reminds you a little bit of like the early advent of computers, right, that you see on the left-hand side. Well, this changed in 2016 when we created the first programmable quantum computer in the cloud. And we allowed people to sit in front of the computer, and you're seeing a screenshot there on the right-hand side. And you can, if you look a little bit closely, you would see these quantum circuits. And then people could drag and drop the early version, these gates into this pentagram-looking structure that contains the circuits. And you could click run, and it would just sort of automatically execute behind the scenes. And that has been an explosion as a consequence of that, of a new quantum community of people learning how to program these systems, with over 500 scientific publications using the system. And now we run close to 2 billion quantum circuits a day. So this is what we did. You sit in front of your computer, you program your gates. We send the zeros and ones over the internet. We convert them into microwave pulses that you see here that operate about 5 gigahertz. We send them down the cryostat to near absolute zero. It creates a superposition, entanglement, and interference operation inside the qubits. We take the signal, we amplify it through quantum limited amplifiers, and then we convert it back to zeros and ones, and we return the answer to the user. Incidentally, these computers are the most beautiful computers that we've ever built. You see the inside of these quantum cryostats is here. These beautiful superconducting coaxial wires. Just as a little a zoom by, so you see what it looks like. This is where those microwave pulses travel down, and you see at the very bottom that shiny square. That is the quantum processor itself that contains the qubits themselves. So this is the explosion of what happened in the quantum community. You're seeing since May 2016, these are the people who are actually running quantum circuits and executing them in the quantum hardware. We've built since 30 plus quantum computers. We have at present over 20 quantum computers online on the IBM cloud. And one of the things I want to highlight that is in the end, we realize the fact that, for software developers, for many of them, they're not going to want to know all the details of quantum physics. And in the end, they're just going to want to be able to write their programs, right? And to be able to benefit from this resource. So the future that we see for quantum computing is one of frictionless development. And what we mean by that is, you're not going to need to learn a new language. You're going to be able to enjoy writing in Python or whatever you like. Behind the scenes, there will be libraries of quantum circuits that will match to the right algorithm that you want to be able to accelerate with quantum. It will get mapped to the right quantum computer to execute the operation, and then sort of transparently translate it back to the developer. I mean, just to show an example that may seem a little bit ludicrous at the moment, but we've demonstrated, is that you could integrate it even into no-code environments, like an Excel spreadsheet, where behind the scenes there will be quantum operations that could run everywhere. So the future that we see in here is one in which it will be embedded in industry workflows. And to be able to make progress on this, we're going to have to pay a lot of attention to the quality of the circuits and how well they get implemented to realize value, the capacity, how many of these circuits can we run and how fast, and the variety. can we apply them to a whole set of problem areas, optimizations, machine learning, chemistry, etc. So I'll just touch very briefly on this topic of capacity, because it's going to be very important to realize that to be able to run any practical application, you're going to need to run hundreds of millions, perhaps even as many as 1 billion circuits. And this is something that is growing exponentially. As I mentioned, we run close to 2 billion quantum circuits a day. And we envision that by 2030, behind the scenes of the world of code, there may be as many as 1 trillion quantum circuits running behind the scenes. And the people that are going to, be able to develop this world, they will be kernel developers. These are the people who are going to need to know all the details all the way down of implementing pulse level controls and timing controls on these quantum machines. Algorithm developers that are going to build the building blocks like state preparation operators and oracles. They also need to know things about quantum physics. And then there's model developers who will not need to know quantum physics, but rather describe the problem in a way that can benefit from quantum computers. We have laid out a roadmap for what's going to happen this decade that we're going to drive, including building machines. This year, we will deliver a 127 qubit machine. Next year, 433. And in 2023, over 1,000 qubits. And a whole software stack that includes both runtime environments as well as pre-built quantum libraries that will be able to have applications for finance, optimization, machine learning, and the natural sciences. And I would share before I close to you something that we're really excited about, which is we've created now a Cascade Runtime that has demonstrated over 100x improvement in the efficiency with which we can run these quantum circuits. And I'm going to play you just a short 1.5-minute video explaining what this looks like, and then I'm going to close and we can have a dialogue. So let me show it to you.
For this problem, the first step is the user needs to define a molecule and its electronic structure. The next step, the user needs to specify the quantum program and the circuits that will be used. Then the user constructs the BQE program that they want to run. This is based on the Cascade Runtime as we talked about. Now they simply just call solve. So now here's where the fun starts. The quantum computer is now this quantum system plus a hybrid classical server plus the user's computer. Let's start with the user in San Francisco. The runtime program now goes to the user's computer through the cloud, and it actually, in our case, goes to the IBM cloud that's in Austin, where it's authenticated and sent to the IBM Quantum Data Center in Poughkeepsie. Here, the runtime manager starts. It sets up this new container program, and this does the classical computing and it makes the circuits to be run. As you see, there's lots of circuits that are being sent to the quantum systems. These are run on our quantum systems, and the results come back, and you'll see there's lots of zeros and ones. Now it goes to the classical server again, and it processes those results. And if the algorithm calls, it resends those circuits through to the quantum system, and it comes back again, processes the results, gets the final answer, and sends it back to the user that's in San Francisco. And now they see, as in this example, the chemistry plot.
So this has resulted in a very, very significant improvement in the runtime. And this is what now is being explored by a very large collection of institutions all over the world. We have over 150 members who are part of the IBM Quantum Network. And you're seeing here listing examples of applications that are being explored with these libraries of quantum circuits. So let me close right now that we touch on these, two dimensions of the neural network implications to AI and code, qubits, and perhaps in a different time, we can also talk about the implications of the convergence of bits plus neurons plus qubits, which to me is very, very interesting to imagine these workflows of this heterogeneous integration of these environments. And I gave you two examples in terms of open source activities that perhaps you would consider also participating and joining. One is Project Codenet, right, on AI for Code, and the second one is Cascade through cascade.org. So thank you very much, and look forward to the dialogue.
Applause. Thank you very much, Dario. There are some questions in the chat. They are both on quantum and on the AI part, but the ones with the most votes start with the quantum. So let's start there. And the question with the most votes is by Grace Lewis. While the promises of quantum computing are huge, it seems that we are very far away from quantum computers being able to solve real-world problems. In your opinion, how away are we really?
So it's a great question, right? And what I see is that I think that demonstrations of practical use of quantum computers, of things that you cannot solve classically, is definitely going to happen this decade. I feel very strongly around that. I think we have a high probability that some initial demonstration may happen before 2025. We're driving very, very hard this roadmap of demonstrating an inflection point in terms of the error rate progression, scaling them through software and not just through the device limitations, come 2023, 2024. So we need to be able to get, for superconducting qubits, just to give us an example, we need to be able to get to 2-qubit error rates of something like 10 to the minus 4. We've demonstrated already 10 to the minus 3 error rates. So there's a factor of 10 that we got to do better around that. And then you got to be able to integrate them into large systems and be able to be very sophisticated doing blends of error mitigation and error correction techniques. So what is, historically, if you just say the only path to deliver value is to build a fault-tolerant, quantum computer with millions of qubits where you're implementing the surface code, at scale, that feels very long, right? It feels like that's going to take a decade plus. But the approach we have taken actually is one that combines, I call it 3 cultures: a culture of science, a culture of agile, and the culture of the roadmap. And you iterate to the community together, right? Building and deploying systems and allowing the creativity of improvements of error mitigation and error correction and algorithmic improvements with the machines you have today. So I give you some of the dates that I see. I think there's a lot of challenges, but I don't see this as 20 years out.
Okay. Justus Bokner has a question also about the quantum part. In your opinion, what will be the biggest differences between quantum software engineering versus traditional software engineering? Is a different mindset needed?
Yes. So there's a great quote from our head of our quantum program in my team, Jay Gambetta, where a number of years back, he was discussing with some of his fellow colleagues here in IBM Research who were in the more traditional sort of software side. And at some point he got frustrated and he says, "You're thinking too classically." And we make stickers, around that, to put on computers. And indeed, look, to be able to benefit from quantum at the level of a model developer, you don't need to, think that different. You just need to know that this resource is available to you and that you could do something different. But if you are an algorithmic developer or a kernel developer, you need to think differently. And you need to be able to be educated. And Ari, I know we were talking a little bit before we started the call about the need to educate and train computer science students on quantum. And because I do think you need to look at problems anew with a different, fresh set of eyes, given the sort of informational representation possibilities of quantum. And if one thinks too narrowly or too traditionally around that, it's unlikely that the breakthroughs are going to come from that. So I think that presents a wonderful opportunity for the next generation too, right? To be sort of native in this world and that they see this as something very organic on how to think about these problems.
Then there are also some questions related to the AI part. So let me ask some of them. There's a recent one by Leandro Minku. In the early 2000s and earlier, researchers were investigating the possibility of using AI to do programming. Now, with the advances of AI, computing power, and the availability of data, people are talking about using AI for programming again. However, the mindset is different because there is a better awareness of the strengths and limitations of AI. What would you consider to be the main similarities and differences between what people were trying to achieve in the early 2000s and now?
Well, I think we've had the advantage of these sort of the demonstration of these very large data-driven approaches to it, and recent advances of what we have seen with the world of embedding transformers and all of those things. So the application of NLP at scale to be able to do some of this is a difference than we didn't have the techniques in the past. So I think we would have relied a lot more on formal methods on things of the sort, I think, in the past, compared to a much more sort of like data-driven, large NNs approach to it. Look, there's no panacea. I mean, that's one of the hardest problems in the world, right? To be able to do this. So again, I think we should view it as a continuum, that we know that this is another toolkit in our arsenal, but we know that if you can curate very high quality data sets, look, progress in AI is driven, data trumps algorithms all the time. So very high quality, well curated data sets for code is another thing that we have available. The continued explosion of open source, the continued explosion of examples with which to solve problems, and the fact that those repositories can be more widely available also create for us a new opportunity to do this large-scale curation. And I think that that's what's different. We didn't really quite have that in 2010 at the scale that we can have it today. So those are changes that I think are meaningfully relevant.
Then there's an interesting question about licenses related to Codenet. What if Codenet includes GPL code? Would it make its results, the neural nets and their outputs, GPL?
I know there's actually a lot of nuances about what code set you can use and the right licenses. So that's something that you need to be able to pay. It's a good point. You have to pay a lot of attention to that, because it's a minefield if you cross those wires.
Yes. Then there was another question. Well, let's go back to quantum. Patricia Lago asks, are there investments in decreasing the huge energy footprint that quantum demands?
Actually, I think the energy footprint is very positive compared to classical computer. If you look at the amount of energy consumed on supercomputers to be able to do things like chemistry calculations and so on, right, with these football field sizes on the things and a massive consumption. We build self-contained quantum computers, and we've even deployed in places like Germany and Japan and so on, and they consume about 15 kilowatts. So it's actually that's one of the attractiveness of it. It's actually that it is for the amount of computational space that you're going to be able to access, the Hilbert space that will be available to you, and what you can do, it's actually very energy efficient.
Then there is a question from Marika Huisman. For GPUs, developers still need to understand the hardware to develop efficient software for it. Why do you think that for quantum, it will be possible to automatically find the optimal mapping from the program onto the quantum circuits?
No, so that's why I made the distinction of the layer on those three layers: kernel, algorithms, model developers. Kernel developers and algorithm developers, they absolutely need to know the hardware, and they need to know, not just the hardware and quantum mechanics, right, to be able to actually be able to contribute around that. There's no magic solution, but we also know the power of abstraction, right? So once that crowd makes real progress, our commitment is to abstract it sufficiently such that then the vast majority of developers need not worry about it. But somebody needs to worry about it and do all the heavy software engineering that is required to enable that.
And maybe back to AI, the first question asked, wondering what are your thoughts about AI for data? Because there's a lot of noise and problem in the data at the first place.
Oh, yeah, great question. Actually, that's an area that we are, we've made lots and lots of investments and we're huge believers in. If you look at the average cost of an AI project, 80 to 90% of the cost of actually deploying an AI system is on the data prep side of the equation. So then it's a great question to ask yourself, hey, for all the attention that people pay to the model itself, how about the data prep piece, and how much can you automate around that? And it turns out that you can do a tremendous amount to be able to look at it as a life cycle of data science, right? And what happens throughout, and how much can you automate the data prep steps? And the answer is you can do a great deal. And actually, it's one of the best ROI efforts that you can do is to concentrate your energy on the data science and data prep part, like most of the headlines is always about the models, but really is the smallest and in some way the easiest part of the whole problem. is that one. So yeah, great question, and that's definitely where there's the most return for investment.
Wonderful. We have 20 seconds left before this meeting will automatically close. So another round of applause. Thank you very, very much.
Thank you.
If it were a real meeting, you would have gotten a real present, something original from Madrid. But, now it's virtual. So applause, applause. There will be a continued opportunity for all participants to chat with Dario. So there will be a separate room popping